Did you know that the term shift left was coined way back in 2001? How many times have you heard those words since then? For me, maybe 1,000, especially around conference time. And today, we're talking about shift left again, but maybe in a different context than you have thought about before. We're talking about shifting left with Calibre. Yes, the Calibre Design Solution Suite from Siemens. But I hear you loud and clear, my engineering audience. But isn't Calibre just about DRC? Well, that may have been true in the past, my friends, but now we're moving Calibre into our design and implementation flows as well. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, David Abercrombie from Siemens and I investigate the details of Calibre's shift left strategy. We take a closer look at how the tools and techniques of this design tool suite can help reduce sign off iterations and time to tape out while also increasing design quality. And before we get started, don't forget to click that link. There you can find even more information about this topic from Siemens. Hi, David. Thank you so much for joining me.
Thank you, Amelia, for having me.
Absolutely. Okay, so the term shift left has been used for a long time to mean a lot of things. But, David, what exactly does Calibre mean by shift left?
That's a good point, Amelia. It has been used forever in a lot of industries in a lot of ways. And I think probably in this particular case, we could think of it in two ways. First of all, kind of shifting the way people think about Calibre to begin with. In the EDA industry, I think Calibre has become over the years almost synonymous with DRC. It is like the de facto standard and what people initially always think about. But if you really look at the portfolio of what Calibre Design Solutions offers, it's a lot more than DRC. And I don't just mean under physical verification. Obviously, there's a lot of things under physical verification beyond DRC we've built up over the years and are continuing to build. But there's circuit verification capability, there's reliability verification capability, and then a fundamental suite of interfaces that allow you to use all these tools in useful and integrated ways within all the third-party design implementation tools and various things, such that it's really become like the ecosystem for all of the EDA world, whether they're design customers or OSATs or foundries or IP providers. It's an ecosystem suite of tools that's a lot more than just what people naturally think of as DRC. And then following on with that, I think the second shifting of thought is kind of how people would normally think about using Calibre, both what for and where and when to use it. Looking at this diagram here, in the traditional, I think, mental model that most people probably have over the years is if you're doing a design flow, designing cells, blocks, chips, or whatever, it's obviously an iterative process that you go through and building it up and getting it complete. And most people, I think, traditionally see that as, oh, that's something you do in design implementation, that you build and check and integrate and build up and continue to iterate until you think you're about done. And that's where people, I think, tend to traditionally think about Calibre at the end. Okay, I think I'm about done here. Now let's run Calibre because it's the sign-off standard, and we'll see if everything's actually okay. And that's great. Definitely we are that sign-off standard. But what we really want to do is shift left, is shift people into thinking about, no, Calibre has been built and extended with the idea of using it all during that design flow as you do each of those iterations with the goal of both bringing that sign-off standard verification up into the iterations that you're doing, but to then provide capability and functionality that helps those iterations run faster, debug faster, give you quicker results, and even reduce the number of iterations such that the entire schedule or the time it takes to do that design function gets reduced. And so by moving these capabilities that people have come to trust over the years up into the design and implementation of flows, and then adding new capabilities and even leveraging artificial intelligence to make them work better, we really think that is what enables customers to more significantly compress their cycle time and increase their design quality.
Well, that sounds like a great potential benefit to your customers. So, David, how exactly is Caliber making this happen?
Well, that's a good point. We've had to build and are continuing to build lots of extensions and capabilities in the tool to make this integration and shifting this into design much more feasible and much more practical and give it much more leverage and utility. And we've focused our efforts in what we're calling the 4 pillars of development, as shown here in the slide. And the first of those is we're called verification optimization. And that's just where we focus on extending the fundamental capabilities of the platform. What kinds of things can we check? What ways can we check them? So it's building the fundamental infrastructure that lets you check things that you never could check before, or check them in better ways, more accurate ways, simpler ways, and so that we cover the gambit of what's possible to be looking at during design. The second pillar is optimizing the execution. When you're running all these tools, making that easier to do, making that integrated in the design tools that you're using, making them run more efficiently, focusing them on only running the things that need to be run at that point in time, those kinds of things. The third pillar is once the tool runs and gives you issues to look at, helping you with the debug of those issues, making that more efficient, more practical, getting you to root cause faster to make it more effective. And then the final pillar is really a little bit of divergent when you think about Calibre. It goes beyond just verifying and finding problems, but saying, well, this is a powerful engine that can process all these polygons and do all these things. Why can't it actually help in many ways to fix or enhance my layout to be better, more yield, or get to final tape out faster? So that's kind of a whole new pillar.
Okay. So, David, can you provide some specific detail about the kinds of things Caliber is developing in each of these areas?
Sure, yes, they're extensive, and I think it would help dive a little bit deeper. Let's start looking at that verification pillar, optimizing the kinds of things you can check. What we've been building over the years and continuing forward is trying to extend beyond the classic idea of just measuring edges and determining something is basically this wide or this much area, that kind of thing. And the initial stages of changing that paradigm was introducing equation-based checking, where you have multidimensional mathematical equations that can take measurements from a layout and determine whether something is good or bad or better or worse. And then we extended that to include pattern-based checking, things that you can't write traditional derivations to find problems, but basically take a picture of it and say, does it look like this or not look like this? And all kinds of tools and capabilities associated with comparing things to patterns. And more recently, we just released the ability to embed ML models within the checks that you develop. So even as a foundry or somebody who's writing checks, if you have new phenomenon you want to check that you can really only express as a function of a machine learning model, build infrastructure to train and run those models in the deck with all the other checks. And then, of course, we've got layout circuit aware checks like PERC that kind of connect physical and electrical things together. And more recently, we're really trying to expand reliability checking to include whole new categories of things we've never checked before, like power analysis, thermal analysis, stress analysis, new things that have traditionally been ignored or just cross your fingers and hope you find out what happens in silicon. And then finally, the industry is moving away from just rectangular shapes to things that are curves. And we've got to extend abilities to check things that don't follow the traditional look and feel of designs. And as we move on into the execution pillar, again, this is making it run more effective and easy to use, helping you more intelligently configure the runs, pick the resources that would make this run more optimally and give you a better runtime, better utilization of your hardware, helping automate the selection of what even to run at this moment. Where am I in the design flow? What should I be looking at this point? What should I be ignoring at this point? Automating that, helping with your ECOs as you iterate, realizing what you just did before. What can we automate to do the second time, learning from what you did the first time, and advanced interfaces to help with all of this. So all of this is focused around helping me set up and run the jobs much more efficiently and get better run times and quicker results. And then moving to debug, that space, it's all about weeding through the noise of what's there, all the issues that get found, automating filtering of things. These errors have already been waived or need to be put aside or separated out. to create debug signals where we look for patterns in the results that say these look alike. These look to be caused by the same types of root causes, whether that be DRC or LVS, trying to help get to root cause faster. Automate generation of those things, and even trying to build capability for you to annotate what you're finding so you can learn from it, and building brand new interfaces for visualizing all of the errors that you see. That final pillar about correction, which is probably the most divergent from the traditional view of Calibre. We've had some solutions in the past that people are sort of aware of that you can use to manipulate layouts or do fill, those kinds of things. But more recently, we've been building automated tools that know how to do basic design optimization things like the insertion or filler cell insertion, those kinds of things we can do automatically. And we're working on solutions to dramatically improve automated correction of antennas. And of course, all of this Calibre correct, since we know what's legal and not legal, and automatically back annotating the changes into your design tool, so it doesn't have to happen outside of your normal design flow. So those are some of the details of each of those pillars, the kinds of things we're developing and the breadth of them and the wide assortment of things we're trying to build to make all this work.
Excellent. Now, David, that was definitely a lot more than just DRC. But how does developing all of these capabilities shift left the day-to-day experience for a designer in a practical sense?
Yeah, I think that's where the rubber hits the road, right? I mean, it's easy to say shift left or, infer some meaning with that, but I think it would probably be easiest to use an example just to kind of illustrate how we think this can make a big difference and the level of difference it can make. Let's just pick a portion of the normal design flow. In this example, we'll use block placement. So this is a block designer who's doing initial placement of the macros and cells to put this block together. And if you look at the flow on the left, which is kind of the traditional way people have done this over time, it's not a one-step process. It's an iterative process where the designer will do an initial placement of the macros and cells. And of course, in the beginning, the macros are just instantiations, or they're just being developed and they have all kinds of errors of their own, which the block guy really isn't interested in at this point. But they place them, run the DRC tool that's built into the P&R tool where they're doing all this. It's flooded with errors within the block, outside the block, the interfaces where they're doing the placement. It takes forever to run because there's so many errors. Weeds through those, finds the ones he's really focused on, does some correction, iterates again, does an updated placement, runs it all again. Well, now maybe the macros are finished, but they had waivers that were errors that are okay to be in there, but they still show up in the DRC and has to look through those and iterate again. And maybe finally after 3, 4, 5 iterations, that part looks DRC clean. Then you got to do your decap filler cell insertion. So you use the tools that are built into the P&R tool to do that. Iterate, check the DRC, couple issues you got to correct, do another iteration. And then finally, you're probably going to do the base layer fill to fill in all the open areas, use the fill tools in the P&R tool, iterate the DRC, go through that a couple times. And then finally, it says everything looks okay. And this is where traditionally people think, okay, now it's time for Calibre. Even though we ran all this DRC, we're going to sign off with Calibre, run it, and lo and behold, it says it's not clean. That's because there's discrepancies between the DRC tool being used in P&R and the sign-off tool in Calibre. So they got to go back, iterate a few things in placement or fill or whatever, clean those up, and then finally run a final DRC Calibre job that says you're good to go. Now, you can see it's a messy flow, lots of iterations, lots of things to deal with, but it's what people have been living with. And the concept of shift left is to change that dramatically, as you see on the right. Calibre is not something you do at the end. Through our interfaces like real-time digital, you can run Calibre, all our Calibre tools, right inside the P&R tool. You don't have to stream data out, run it in batch, look at the results externally, then go back to your P&R tool. Everything can run integrated into the tool. So right after that first placement, you're running the sign-off DRC tool. And with the extensions we build for things like Recon with Graybox, you can have it automatically ignore all those macros that aren't ready yet, that are full of errors, and have it only focus on the DRC issues at the interfaces that the block designers actually care about. And so it runs faster. They weed through all those results because there's so many fewer, much faster, and get to the second placement. And that second run, now the macros are clean, but there's waivers. Well, we can auto-waive all those so those errors don't even show up, so they're not distracted by that noise. Make that iteration faster. Now they're clean. Calibre says they're clean. And then when you get to doing the filler cell and base layer fill stuff, we have new Calibre tools that can do that using the Calibre engine. And what we find with those tools is they run faster, they do a better job of doing the fill, and they're inherently DRC clean because the Calibre engine is the one that's running them. So you can do them back to back without doing a DRC in between. You run that final DRC run with Calibre, still inside your P&R tool, and everything's clean because it didn't make any new errors. And then like all the new verification stuff I talked about, building things you could check now using Calibre that you probably never thought about checking before. I just put an example of one here in this flow at the end. Maybe one of the macros you integrated into this block is a compiled memory or some piece of third-party IP that you pulled in and integrated into the block. And DRC may say that it's clean. I mean, you didn't break any rules in integrating it in, but did potentially something go wrong that you did by accident or as part of importing it happened where something got dropped or slightly modified in a way that's not DRC illegal, but made it such that that piece of third-party IP is not actually what it was certified to be. So we have this new tool using pattern matching where the third-party IP providers give us the patterns to check for, and we can check that IP against those golden patterns and say, yes or no, it looks like it's supposed to look. You haven't accidentally made a mistake. Otherwise, you wouldn't find that out till you got to silicon. So again, that is shifting left's a problem that wouldn't reveal itself till silicon, all the way up into initial placement of the block. So, you can see that this whole concept of moving these trusted Calibre tools from the end up into the implementation cycle is what really, we believe, compresses the cycle time and gives you better quality and better results much faster. And fundamentally, Amelia, that's what we mean, and that's what we're trying to accomplish.
Excellent. Well, David, I think that's all I have time for today. Thank you so much for joining me.
Thank you so much for having me, Amelia. It was great.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Siemens. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talks section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.